The structure in the data is important in the sense that most of the data that we have is unlabeled. It's arduous task to label the data. So if we can understand the structure, maybe it will help us understanding the label, and we can move towards some kind of learning that can be done without labeled data or few labels, and then added the knowledge of structure, we can do some kind of semi-supervised learning and so on. So from the realm of supervised learning, we want to move towards unsupervised learning where we don't have labels. And for that, the type of learning that we do is called cluster analysis. Clustering gives us the structure in the data. We will visit two of the famous techniques today that are being used. The basic idea there is that every data is coming from a domain, and the knowledge of that domain help us identify two things if they're similar. So the notion of distance between two things comes from the domain. There will be many distance matrices, and each is not suitable for all. We have to decide. First key thing in clustering is to find out the appropriate distance metric. And then, since it's not labeled, before we could do with label data lots of sum of squared errors, accuracy, precision, recall stuff. But now we don't have labels. How do we evaluate the structure that algorithm has found? Is it the real structure in nature of the data or the domain? It's hard to evaluate a clustering solution, but we will look at a few techniques that can help us have a sense of goodness. It's first part, partitional clustering. I'm sure you have watched this animation, Wall-E. In this particular starting of this animation, the guy is collecting stuff and putting them together. And since he doesn't know what is what, he looks at the things, looks at the features, and tries to put them together. So where shall this fork spoon go? It ends with, if you remember, the robot puts it in between both the clusters. Numerous applications in data compression, image compression, missing value estimation, anomaly detection, we see clustering in action. In first technique that we are going to do is part of partitional clustering family. We look at data as divided into by these linear boundaries, kind of linear. And each boundary creates a cluster where all the points are centered around centroid, the textbook word that they use. The centroids make a limitation on partitional clustering algorithms, and that limitation is that from the name of it, center of something means that something is going to be spherical or circular, right? But what if the clusters are not circular or spherical? They have nonlinear shapes like sign of Pepsi or yin yang. In that case, it will be challenging to correctly identify the clusters, but as long as things are spherical, which are usually in nature, things are spherical, the blobs or the objects, they take a symmetrical spherical shape, so partitional clustering works well. The algorithm, basic one, is k-means clustering that asks for k. We assume there are k clusters, and then we randomly pick as many data points from our data set and say that these are our C's or centroids, and then calculate distance from each data point to those selected data points, C's. And based on those distances, we appoint or assign each data point to the nearest C. Now, the nearest word is keyword here because how do we measure nearest is going to shape the shape of clusters. Based on that appointment or assignment, we recalculate C's by taking the average of all data points, their coordinate. We take their average and we get new clusters. We repeat 3, 4, 5 until this assignment doesn't change the position of C. Visually, let's say we have these data points. They look like two clusters. So we can start with K equals 2. We take distances, and for this center, these points are nearby. So we compare for this data point, the distance between this center and this center, which one is smaller? This one is smaller, so we assign this to this red cluster like this. So all data points get assigned based on the comparison of distances from initially picked cluster centers. So picking is one free variable or degree of freedom. If we picked these two, cluster shapes will be slightly different. If we picked randomly, these two cluster shapes will be different. So picking the initial point does have implications on final clusters. That's why we run the data through the algorithm multiple times, and once we get similar shape across multiple runs, we are satisfied that this is the structure behind the data. Iteration 2, based on these appointments or assignments, the cluster centers will change at the end of iteration 1, and based on these new centers, we again take the distances and reassign. This time, even though we took the distances and reassigned the points, this time the movement is very small. New cluster centers moved very little. When the movement is less than a small number, then we stop. So do we need to do iteration 3? Depending on the movement, we can say, okay, the center points are just jiggling around. They are not taking strides. So we stop and come out of the loop. And that's all there is for this example data. We know it's age data. We assume there are two clusters. So we randomly pick 16 and 20 to take the distances. So based on the first iteration, we compare distance from 16 is 1 and 7. So 15 will belong to this center, this center, this center, this center. First three values belong to 16, others belong to 22. And then we take the average of these points again that belong to 22. Average of these points move the center to the next 36. When we take 36 as centroid, then many other points that are far from 36, they belong to 15 now. And this is how these clusters get natural shape. Third time in third iteration, the centroid for this cluster moved from 33 to 45, and this one moved from 15 to 18, and we get readjustment of members, few members on this boundary. And that's all. After that, they will not move much. And if we use K3, then for sure we are going to have some kind of teenagers, middle age, and after middle age people. But how shall we decide K is 3 or 2 or 1? That's a heuristic question, and it has a heuristic answer. We will look at that. But for now, there is one thing that we can easily use, and that is the error. We don't have true labels, so error is going to be the distance between actual value, let's say 40, and the centroid 47 squared distance. When we square this distance and add all squared distances, there is a heuristic. For all k's, the sum of squared distances for all the data points from their corresponding centroids is going to be the reflection point on this elbow diagram. So on x-axis, we have k 2, 3, 4, 5, 6 up to 14. And for 1, SSE will be the largest. And for larger k, it will be the smallest. Maybe over here in every cluster, we have just 1 or 2 data points. Over here, all the data points. We find the elbow point for this. So around that elbow point, 4, 5, or 6 are the natural kind of clusters in the data. That's why it's called the elbow method to select k. So just like in the beginning, I said, we run the data through the algorithm for multiple iterations with different initial points. Here, we run it with same initial point, but we change k. So we are having 2 now degrees of freedom, initial points and choice of k, which changes the ultimate result. But the elbow method will help us identify. So this k5, is going to be giving much better clustering than earlier or later case. The other natural kind of intuitive way to evaluate clusters created by k-means or partitional clustering algorithms is this heuristic. Intercluster distance is larger intra-cluster distance than intra-cluster distance. So the green arrow is larger than the small blue and red arrows. So in comparison, right-hand side is preferable than the left-hand side. As long as we keep this heuristic in mind, whatever k gives us this, if k3 gives us this and k5 gives us the left-hand side, we will prefer 3 because 3 gives us larger intercluster and smaller intra-cluster distance. Now, intercluster distance measurement is tricky. There are 3 possible options. We can either choose the nearest points in the both the clusters or the farthest points. For the nearest, we say single linkage distance. Farthest is complete linkage. Or we can take the average of both clusters and use that distance to measure intercluster distance. So in summary, k-means clustering is one of the partitional clustering techniques. Here we are assigning as our data point into one or the other cluster. It can be probabilistic. We can say 0.3 this, 0.7 that. Soft assignment. And choosing the k, we can use elbow method or the heuristic, which makes sure that the between cluster distance is larger than between the data points in a cluster distance is smaller than the distance among the clusters in interclusters. So the evaluation, it's tricky, but as long as in the domain, in the nature, the clusters are spherical, we are good. If they have a nonlinear shape, then k-means clustering cannot meet that challenge.